Today we're going to talk about bonds, chemical bonds. And all of your notes you're not going to have, there's some stuff you're not going to have to write, so just pay attention. The directions on the screen will tell you which to write and which not to write. We know that atoms are the smallest unit of matter that is still considered matter. They are indivisible. So what do you think indivisible means? And I'll give you a hint. Divide. Root word is in there. Now, the electrons we know are spread out in different energy levels. Sometimes they're called shells. So if you notice here, the screens on the instructions are going to tell you that you're going to add the green words into the blanks. So we know that the atomic number, not only is it the number of protons, but it tells us the number of electrons. Electrons can vary in the amount of energy they possess, and they occur at certain energy levels or the electron shell. So, level 1 has a certain amount of energy, level 2 has a certain amount of energy. The outer shell, or the valence, determines how the atom behaves when it encounters other atoms. Electrons are placed in shells according to the rules, and we worked on these rules yesterday, that first level can only hold 2, the second level can hold 8, the third 18, the fourth 32. If you look, we've got 4 different examples here. Hydrogen with its 1 electron, carbon with its 6, 2 in the first level, 4 in the second, nitrogen with its 2 in the first, and 5 in the second, and oxygen with its 2 in the first and its 6 in the second. The octet rule tells us that atoms tend to gain, lose, or share electrons, so they have a total of 8 in their outer shell. All atoms want to be like the noble gases and have full outer shells. So if carbon has 4 valence electrons, because it's in column IV, how many more does it need? Nitrogen, column V, has 5, so it would like to have how many more? And oxygen, in column VI, has 6, so it needs how many more? So drawing the models can help you see how many more it needs to make 8. The positive and negative numbers you see up above on my chart help you figure out how many, when they do bond, are they going to end up with more protons in the compound or more electrons? So the negative and the positive side give you the hints. We'll get to that. Now, why are electrons so important? Well, they have different configurations. In different configurations, that just means how they can bond. And we drew these Bohr models yesterday. We practiced. You did the whole second row. So we're going to pause right here and let you check that second row, which is on the back of your task sheet. Remember, we only checked the first side when we were going over this. So I'm going to pause right here and let you check. Now, there are different types of bonds, and it's going to tell you how it's going to happen. In ionic bonding, the ions, when the metal is losing that electron and ends up with more positive particles, and the nonmetal is gaining that electron and ending up with more negative particles, you've got this, you're no longer electrically neutral, and that's what an ion is, this process of where they're giving or taking the electrons and upsetting that balance of protons and electrons. And so there's actually a giving and a taking. So metals are going to transfer 1 electron or more to a nonmetal, and when the nonmetal accepts those extra electrons, then we have an ionic bond forming. So there's actually a movement of electrons between metals and nonmetals. And the electronegativity, again, is how much energy the electrons have. And this charge, this positive and negative attraction between the positively charged metals with the extra proton and the negatively charged nonmetals with the extra electron causes the atoms to stick together and form this new compound. They're weak bonds. They can be dissolved and broken through another chemical reaction. They do form what's called a crystalline lattice. So it's a repeating structure. If you look at, say, an atom of a molecule of salt under a microscope, you can see this regular repeating geometric structure. So sodium chloride, calcium chloride, potassium iodide would be examples of ionic bonds. So again, metal to a nonmetal, and I can identify the sodium as the metal and the chlorine as the nonmetal. So we've got the attraction between that extra proton and that extra electron, and it causes them to stick together and form the molecule. That's another visual in that there is one given away. And then here is the Bohr model drawing. Shows that sodium has the single electron in its outer level. It gives it to chlorine. Chlorine now has more electrons than protons, and then that makes the bond. And you would call that sodium chloride ion. So here is the regular repeating crystalline structure of sodium chloride. You can see it is geometric. It is very square shaped. Now in a covalent bond, the prefix co means share. So if you live in a co-ed dorm, there are boys and girls there sharing space. If you are co-chairman of a committee, there are two of you sharing the responsibility, co-presidents. And valent means outer level. So literally you are sharing electrons. This only occurs between two non-metallic elements, so two non-metals. They are strong bonds. When you're naming covalent compounds, there's some rules for naming, adding prefixes. They have low melting points, so they change from a solid to a liquid at not very high temperatures. They have very strong odors for the most part. If you want to think about, say, opening a bottle of rubbing alcohol or a bottle of ammonia, you are hit by the odor as soon as you open the container. They're also volatile. They change to a gas very quickly. You leave a bottle of ammonia or rubbing alcohol open, within hours you'll notice that the level of the liquid has gone down because of it's volatile, it's evaporating. They form all of your polyatomic ions, and we're going to get to that next week when we actually figure out how to write the formulas in these bonds. And the diatomic molecules, which are the twins of the periodic table. So there are 7 nonmetals that are never found in nature as a single element. They're called the diatomics. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are the diatomics, and that's on your periodic table as one of your definitions. So here is a visual. They come together and they share. Notice where they are sharing. That is the bond. And so if you notice again, when they come together and share, if you can count, by sharing, they both have 8 electrons in their outer level. So they come together where they each have 1, and 1 plus 1 gives them 2, plus their other 6 that they had. So they now have 8. Another visual of sharing. When polar and nonpolar molecules, remember when we talked about water, we described it as a polar molecule. In a nonpolar covalent bond, electrons are shared equally. So look at this visual. So the example would be H2 and Cl2. The model you just saw had 7 in the outer level of each, so they're each contributing the same amount for sharing, so a chlorine bond. A hydrogen bonded to a hydrogen, each one brings 1, and that 1 plus 1, they're equal electrons to share. That would be nonpolar covalent. Here, the O2 molecule, they're each bringing 6 to the table, so bring the same amount of electrons to share. Then polar is they're sharing unequally. They're not both bringing the same number of electrons to the bond. So water would be an example. Hydrogen is only bringing 2, 1 for each hydrogen, and oxygen is bringing 6. So there's an unequal sharing. But even though the two were not the same size, they're still willing to share. Water is polar because oxygen has more electronegativity. Remember, it's bringing 6 electrons, and hydrogen is only bringing 1 each. Now, metallic bond is formed between atoms of the same metal. The electrons form a C around the atom. This helps us with metals with some of their properties. They're malleable, they're ductile, they're good conductors, they're lustrous, that means they shine, they have high melting points, and all this is due to their electron configuration. So iron, aluminum, gold, cobalt, they can bond to themselves and form metallic bonds. There's plenty of electrons, and if you think about it, most of your transition metals that form metallic bonds, they have higher numbers of electrons. Look at, like, mercury has 80, gold has 79. So there's lots of electrons to go around. So here's an image of this sea of electrons in the bond. Metals also form alloys. Metals do not bond with other metals. They only would bond with themselves to form compounds. But they do form solutions or mixtures of metals. And, for example, steel is a mixture of iron and carbon. Brass is a mixture of copper and zinc. Bronze is a mixture of copper and tin. And pewter is a mixture of tin, lead, copper, and antimony. So 3 types of bonds. In ionic, there is a transfer or movement of electrons. In covalent, there is equal sharing, and those are our nonpolar covalent bonds. Unequal sharing are our polar covalent bonds. And then metallic, when a metal bonds to itself.